Okay, now I think so. Good afternoon, one and all here. So actually, the topic was given as analysis and public to quality resilience. So healthcare. So I'm trying to share research experiences I carried out. The name in this analysis, we have analysis on each things and how we have come across. In fact, this is one of the DST projects I have worked on. So with DST. So with that DST tied only, all this publication has come down. So it was 40 lakhs funded projects combined with the Ramachandra Medical College. So they are the one who supported us in providing the data. With their analysis only, we are moved forward. I'm just experiences how on with this. Okay. So the top was easy but is for artisans, low level frequency channel contribution. We analyze the EEG signals on this. Okay. So we know it very well. How this was, one is the introduction and second is the mode, how we into this the autism. It's a survey. What are the research still left out? How we need to analyze in that. How to frame for this DST work and also the key of our research along with my references. So this is that. See, so autism is considered as a complex disorder. So according to WHO, it was almost 1 in 100 children getting an autism. I don't think before 25 years and all, autism is a common word across our. Now almost you can see that in 100, more than less than 100 child, one child is getting a need to work out as well. To the economic times, we come across the same thing. In India, it was 18 million people are affected with that. I mean, diagnosed with that. There are some cases where people are not coming for diagnosis, so taken into consideration. So people who come, we are considering that. So about to 1.5 of 9 years. This is like India. So 1 to 1.5 is a very huge number. So we need to, even the 0.1% is a huge number across the billion population of us. So 1 to 1.5% is a huge number as per the number is concerned. So it is need to address in this direction. So that's what the motivation came from. Okay. So the point is that early diagnosis really helps to improve their quality in their upcoming site. Okay. So it will improve us. So here, so far, in the previous slide, I was talking about only autism. And in this slide, I'm using one more terminology called autism spectrum disorder. So what is autism? What is autism spectrum disorder? Autism is a very common terminology where the clinical analysis people will be doing it. However, when it comes to the research level, we will address all the problems with respect to each and every nook and corner. So autism is a very common word, but however, autism spectrum disorder is the actual word. It's a big umbrella which covers many things. So what are the autism spectrum disorder? How the person can identify this child is having a ASD. Short term is autism spectrum disorder, short term is ASD. One is they have motor difficulties, communication difficulties, and they do the behavior repeatedly and sensitive. They will be very sensitive. Some of them won't be sensitive at all. The social movements will be restricted. So all these things are some of the behaviors of the kids from the, we can understand that they may be affected with the autism spectrum disorder. So those are the, because early age, it is very hard to identify and the early age symptoms is. These are kind of symptoms is, we may think that maybe our child maybe grow up, will come up faster. But at the same time, we have to keep our eye on that, whether the speech is coming properly or all those things. The child should not get into ASD trouble. So that also we need to be keen into it. So these are some of the symptoms for my ASD. So as I said, ASD is a sum of a big umbrella. So previously it was separately it was addressed something like RETT syndromes, the pervasive disorder, that PDD-NOS, and Asperger's syndromes, autistic disorder, childhood disintegrated disorder. All these things are separately it was addressed. All these things are causes because of the spectrum disorder in the neurological cells. So how there comes from the autism spectrum disorder. So it's autism ASD is a one big umbrella which covers all these disorders. So through that, because of this disorders only, the behavior of the child is getting affected. So how we are going to address that, all those things, that's not our job. Anyway, doctors are there, they're going to take care of it. So our job is going to be that as engineers, how we can facilitate to the doctors so that they are much more experienced. They are the one to diagnose the patients. We are not to diagnose the patients, but at the same time, what are the research gaps yet to be filled out? How we can aid our healthcare facilities. That's what our main job. So in this aspect only, we are focusing on. So what are the etiology of my ASD is that, what is the causes if you look into it, the brain abnormalities is due to geneticity, metabolic disorders, unstable genes, fever flu during their mother's pregnancy, complications during the pregnancy, all those things that is not under their control. So it is happening means then these are some of the causes why it is happening, what is the reason behind it. This may be any one of the reasons behind it, so we don't know about it. So the point is that if you know why ASD is coming, we can able to go and correct it. But these disorders, these problems, it's not under our control at all. So we cannot go and correct these things. So that's the point what we want to address it. So we cannot correct this at the root level, but however, we can able to correct whenever it is going on. So the current diagnostic method, how currently addressed was, it was addressed through the scale, Indian scale of assessment of autism. Very importantly, if you look into it, it is something like, it's a subjective assessment. Okay. So it's not something like quantitative measurement where like a blood test or heartbeat where you can able to say that like BP where you can say it's a number. However, subjective measurement, so there is no quantitatively can able to measure it. So evaluated by the interaction with the parents and the kids, if you go to the doctors, but purposefully with the autism spectrum disorders, they'll interact with the kids, they'll identify what could be the problem. So based on their analysis, their subjective treatment, they decide that, okay, they'll observe for 15 to 20 minutes and they say that it is a mild autism or no autism or sometimes moderate autism. They'll say that, okay, the range is between 110 to 120, it will be something like a moderate autism kind of things. So all depends on the subjective doctor who evaluates. So there is no, for example, if you take a sugar test, it will be the same thing across if you take a different machines at the same time. However, if you go to the autism test, that may not be the same because that depends on the doctor who evaluates it. There comes the discrepancy. So depends on person to person, doctor to doctor, the evaluation should not differ. There the research problem actually exists. From there only we try to address aid the doctors. We try to give a quantitative measurement. Yes, this person is having such kind of ASD. That is where we address the problem. That is where we got the DST funded project. So that's where we are addressed it. So the treatment currently what's happening was with the MRI image and the EEG recordings for diagnostic purpose we are taking into account. So we are currently analyzing only EEG to analyze all these analysis. So by classification algorithms, what are the image and signal analysis, what are the advanced techniques we have, which is suitable for ASD. So we are addressing it. So the treatment for autism is currently going through therapies, behavioral therapy, cognitive therapy, occupational speech, parental therapy, physical therapy. There are a lot of therapies are there based on the level of, even though we say moderate autism, that doesn't mean that all the moderate autism kids will be behaving same way. Because some people needed occupational therapy, some kids may be needing speech therapy, that depends on the kid. So all those things are currently varying into it. So there is no proper quantitative method to say, hey, this person is this much. We see it here in previously also, the scale wise, we gave the mild autism is something like 107 to 153, which is something like ranges around almost 40 ranges there. So that is not a small range where 40 is a much more larger bandwidth, say the autism kind of thing. It is more than 153 is a severe autism, that's what people come into conclude. So how they are define a number? More than 153 means if it is 200 or 300, nobody knows. So the point is that we need to come to a common conclusion. So how to go across this? So we are trying to give the, from this motivation, we take into account how to facilitate these things. Identifying the frequency bands or how, one thing we are very sure, all our activities are controlled by our brain. So we need to analyze the brain, why the kid is not acting to the situations. Maybe faster, maybe acting much more faster. Why it is happening like that? So all the signals are coming from the brain. Why the brain is responding like that? How to control? That's not our job. That doctors will take care. We'll aid the doctors that, hey, this is how the brain study is there. We need to control it. You do your exercise so that you can come across whether. The point is that currently they do all these therapies, occupational therapy, speech therapy, all those things. After 6 months of time, they'll evaluate it. Again, they give the questionnaires and they're going to check it. Whether any changes happened or not, maybe that day, that kid may not be responding. We don't know about it. So based on that, we cannot say into it. However, we have a quantitative measure to say that scientifically we can say that, hey, the brain is responding, the kid is not responding. Kid is having some other problem. The kid may be have fought with his sibling or his parents that day. We don't know about it. However, what we need to understand is that the brain is responding to the analysis. That's what the main motive. We are trying to address it. So those keep into motivation we are worked on. So all the literature survey work carried out is based on our EEG analysis. What are the approaches there? How they are going for how they address their autism spectrum disorder. I'm not going to explain all these literature survey. So just to show you that we come across a lot of literature surveys, how EEG analysis happen. So from the EEG analysis, what we conclude and what we come across the research gaps and what we move on. So likewise, more than 16 to 17 papers, 20 papers we come across that. From the literature survey, what we analyzed was the research gaps. We went into as a review paper into it. Such gaps, what we understand was, most of the studies systematically do not analyze the EEG by specific brain lobes. So we have the brain signal, that's the EEG, their analysis completely. But they didn't analyze which part of the brain is actually doing what kind of a job. They didn't do analysis based on the lobes. So that one thing we found out as one of the research gaps, because we know that very layman terms, we know cerebrum, cerebellum, all these things part of our brain. So which part of the brain is actually giving such information for motoring skills, for speech therapy, all those things not analyzed so far. From the research literature survey, that's what we found out. Okay, we don't know which part is there, where we need to concentrate on. So that's first thing we found out, which lobe is not responding. And similarly, we found out that EEG signals are much more larger in nature. So out of that, which frequency band is actually contributing for the motoring skills or other speech therapy skills? So we identified it, and that is not that done so far. And the third one was electrode selection. So typically based on technical criteria, so not based on the neural development disorder things. So we looked into it, which one is contributing for more. So I will show you what are the lobes and the electrodes and all those things now. So from there, we'll understand how it has been done. Normally, we know that EEG signals taken from the brain, we used to connect with the brain signals. So in that, these are the three research gaps we found out. One is that lobes are not well defined for the each motoring skills and other skills, and the frequency band which really affects that, and electrode placement. So based on that, they didn't do. So that's what one of the paper what we published as a research reviews. So if you see that objective, we frame the objective as our DST project is that to identify the brain lobes for the classification of ASD. ASD means autism spectrum disorder. Which brain lobe is contributing for ASD? Because whole act is controlled by brain. Even walking is controlled by brain. That is not part of my ASD. That kid may be walking correctly, but that kid may be having speech problem. So if that is the case, I'm not worried about the walking problem. So walking problem is taken care by some part of the brain, while speech is taken care by some part of the brain. Which one is actually contributing for ASD? That needs to be looked into it. That's called the brain lobe identification. That's what we said here. I should show statistically significant difference in EEG patterns. So I will compare the normal kid and the ASD kid. So how it is differed in the brain activities. That's what the first objective. And the second objective is in the frequency band. For the same skill, same job is given to both ASD kid and the normal kid. We say it's a typically developing kid. How the normal kid's brain works, how the ASD affected kid brain works. What is the difference in it? So So that is also statistically proven data. So next is that which channel is contributes more for ASD. As I said, which part is be actually taking care of my ASD stuff. So that is also we will be taking into account. These are the three objectives we keep and analyze, and we give the solution to the doctors. So proceeding with that, this, as I said, this is a combination project with the Ramchandra Medical College. So they are the one we interacted with them. They are the one who supplied the actual data from the kids. We interacted with the people, the students were coming from their parents. From there, with their significance, we went to the ethical clearance. And because whenever we use the medical data, we need to go for ethical clearance. We got the ethical clearance framed by the Ramchandra Hospital. With their consent only, we had taken the sample data. From then we moved on. So that's the one. And as I said, first base thing is that whatever you analysis, data acquisition. We need the actual data. We have the Kaggle data and online data are there, but we don't know how much true is that. We don't know how much real world problem really affects us. That may be still because this also will differ from geographical region to geographical region. If it is for Western countries or Eastern countries, based on that, this culture itself difference, then their behavior also will differ. So, for example, eating in hand normally is quite natural in India, in Eastern countries. In Western countries, eating in hand is a kind of not culturally not well developed. So, we cannot compare this kid to that kid. So, in such scenario, we are addressing our own Indian kids means we need to have the Indian sample data. That's why we aim for it. So, we acquire the data. So currently, we acquired from 10 ASD, autism spectrum disorder kids and typically developing children, and Srihar, that is Ramchandra Institute of Higher Education Research. And the bottom picture is one of the sample kit what we have taken. And this is the EEG signal part what we have taken from this. And you can see that the kit is shown with the laptop. So the point is that the kit was shown with some videos. So that we try to activate this stimuli. We try to give some happiness, some sadness, some fear, some anger to the kid. We stimulate that, so that how the child is behaving. If it is a normal child, if it is a cartoon is coming, if it should be happy one, the child has to be happy. That should reflect in the child's brain. We are analyzing the brain signals. So we are handling those brain signals. One is a normal kid. Similarly, if the kid is affected by ASD, that brain signal won't be different. So that we are analyzing all those things. Okay. So that is recorded with the normal Nihon neurofax machine with EEG signals. This is one. And the first, as I said, the first objective is the brain lobe identification. So how we identified the brain lobe? We identified and we published as one of the paper in the journal into it. So this is the finding the brain lobe things. This is the classification identification brain lobe using Kepstel coefficients. Okay, so before getting into the technical terms, this is how the brain lobes are there. You see that these are the places where we keep our electrodes. You see that here previously that kid is having the points here, the electrodes points. How these electrode points are came up based on these rotations is well known EEG points, and we have 5 lobes associated with that: frontal, central, temporal, parietal, and occipital lobes are there. So across each lobes there are some electrodes are given with it. Frontal lobe having something around 5 to 7 electrodes are there. Central is having 3. Likewise, temporal is having 4. Likewise, they are listed on how many electrodes are there for each lobes. So after these lobes, which lobe is contributing for ACE? That's our first objective in it. So because nothing is done so far that time. So we try to do analysis on the lobe analysis and try to identify which one is contributing for. As we see that EEG is taken for one objective for ASD, and we focus on the lobe identification and we'll move into it. So out of all those things, we take these 7 lobes once, this temporal lobe, parietal lobe, occipital lobe, and each we do analysis. That's how the first objective is gone. So if you look into it, it may look like a big paragraph, but actually if you see into it, one same thing I was repeatedly written. One is EEG signal acquisition, frontal, central, temporal, all these lobes are there. Remaining and all feature extraction and the classifier, each cell segment. That's what I did. So for each lobe was analyzed based on the same methodology. So that we try to see which one is giving the more relevance. So that's what we did. So the same analysis applied on different lobes. So while capturing the data, we don't capture the complete, we capture the complete data, but we also make sure that each channel, which one is contributing, which channel is contributing for which one. So we have separately analyzed each and every data. The problem what initially we had was, we had only convincing the parents to give their sample data. In fact, we are not going to be invasive or anything like that. The parents are had a lot of difficulties to give their data with them, to convince them. We got only 10 kids. With the 10 kids, that's not sufficient to go for deep learning analysis or much more analysis. But with the given data only, we need to move ahead. So what we did was, by showing the video itself, we shown many videos to them. For example, happy or sad, something around 30 minutes, we are make them to say. So that we'll get more data into. So that how the behavior will be analyzed. So that's how we have moved on. Okay. So getting children itself very difficult at the same time. So once you get it, we take more data from the same kids by showing different sets of videos. So in the feature extraction, what we written is in the bracket was 27. These are the 27 features what we have taken. So what are those 27 features was 3 features, 3 set of features, 9 features. One is absolute, delta features and delta features. That is each feature having 9 features from them. And here's LFCC coefficients are taken. Kepstral domain analysis. From the logarithmic based off my Fourier transform, I go for my Kepstral. So Kepstral gives me a clear analysis on my patterns, because we want to analyze not only the frequency range, but we want to analyze how the pattern for one thing. For example, the person is happy, how the pattern of the brain waves looks like. So we want to analyze the pattern so that I cannot compare the happiness of the normal kid with the ASD kid, just like one to an apple to apple matching. But however, I can have that happiness means we know it very well, and happiness means some syndrome, some things will be developed in our hormones. So how it affects my brain? So we try to analyze the patterns. Since I want to analyze the pattern, we went into the Kepstral analysis. So you may ask why we went into, because I want to analyze the pattern behind it for the happiness or any other. I'm not worrying about the emotion right now. The point is that how kid is going to behave for the happiness feeling. So that pattern only I want to analyze with the normal kid to my typically normal to the ASD kid. So for pattern analysis, I'm going for my Kepstral stuff. That's why Kepstral domain, everywhere Kepstral domain only kept. One is the first derivative and another is second derivative stuff. So Kepstral energy, coefficients and frequency domain features and signal energy, delta energy. So with all those things, we take as a features from the 27 features and we give into the different classifiers, KNN, SVM, decision tree and multi-level perceptron. So all this analysis we did, and we see which one is giving the better results for stuff. So with that, when you do the analysis steps was, one is, as I said, I have limited data, but I need to analyze much more. So I already said many more data are much more. We have shown the many videos to them to collect the data. We see that we take the sample short time frame rate, something like 5 total data points as a one frame. We take into it. Likewise, we split all those data. Of course, I need to do my pre-processing by removal of noise and all. Of course, we did that. After doing that, we split the actual data into the 512 data points so that I can compare, I can have much more data. I am not populating the data. With the given data itself, I am having segmenting the data into many different data types. 512 data points, then computing my pre-process, my FFT algorithm in it, and across my filters, triangle shaped window, so I can apply for my 0 to 70 Hz as well as 8 to 30 Hz. I'll tell you, because purposely we did it here itself, because our second objective is to identify which frequency band is going to give my good results. So for cater my second objective, while applying now itself, we try to apply the filters here itself. No other reason. Okay. Then we went for our calculating my log spectral things, linear scale. And for each frame that is 512 data, we applied for DCT to identify. So the same step is getting repeated across all the data to get our features, and we try to give it to the classifiers and give to all the 4 classifiers, and we analyze it. So when we analyzed it, these are the LFC coefficients. The range is between 0 to, you can see that 0 to 70 Hz we have. Okay, and you know it very well. Each band of range is classified alpha, beta, gamma, delta and theta. Delta and theta are earlier, then alpha, beta, gamma ranges are there for the EEG signals. So from 0 to 4 is something delta, then from 8 onwards it's going to be a alpha, beta, gamma. So for alpha beta alone, from 8 to 32 hertz range is coming from alpha and beta. So we have from the literature survey itself, we've identified that 8 to 32 hertz may be giving a good result. So while analysis itself, we had this point, okay, how the 0 to 32 is going to be behaving. That also we had. So next, as usual, our capture energy and normal signal energies are just equations. I brought it here to analyze how we did the analysis part. Then going for my delta, which is the first derivative. Same thing, whatever I have with the first derivative, we went into it. Then we go for my, of course, whenever I go for my classifiers, I need to do my hyperparameter tuning. So for the grid search and all, we did the tuning and we did the cross validation because in order to make sure that our ground truth, the common values, the ground truth values means we do some analysis and how it is matches with the real-time data of my regular stuff. So we do that. So as I said, we do different classifiers. One is the KNN classifier, non-parametric super. I don't want to get into the what is KNN classifiers. We did the KNN classifiers, multi-layer perceptron, decision tree, and SVM, and two more, bad KNN, random forest. All this analysis we made and to identify which one is giving the better results. So when you analyze all those stuffs, what we identified was, we see that one is KNN, as SVM is given here. We see that my central lobe is giving around, can see that accuracy is almost 98.3% compared to all other lobes. All lobes combined together have only 94.9. However, other things are 92, 93, 97, 94. And central lobe is giving 98 in the accuracy level. So we have analyzed the other parameters of the statistical analysis, and similarly across SVM also you can see that it is coming around 98. So of course we did for all other decision tree and other multi-layer perceptron and all. Okay, in all the cases, if you look into it, compared to other things, central lobe is much more behavior, much more good compared to other stuffs. Whether back in as well as the other things and all, this central lobe is always better than the other stuffs. So we understand from this was, yes, when I go for analysis, the central lobe is giving our more results in the AST affected things than compared to other stuffs. So what we understand is that if we look into the previous stuffs, we already come across the 5 lobes, frontal, temporal, occipital, parietal, and as well as central lobes. We found out that central lobe is the one which is contributing for my interval, contributing for my ASD. So that's the one we analyzed. What is the first finding of our things? That itself gives the doctors that they don't want to worry about the other ranges. So they worry about only these electrodes. They don't want to worry about the other electrodes itself. See, why this itself, one of the breakthrough was, the autism affected kids, they won't allow us to keep their electrodes itself because they will be very sensitive. Even the female kids, we have seen that their parents are worried that they couldn't keep the flowers on their child, and the mothers are telling that, okay, we couldn't keep that because I want to keep flower to my daughter, but I couldn't because she is so very sensitive towards it. So the girl childs are not only girls, and many of them are very sensitive to their head things. We should not disturb them. In such cases, there out of 19 electrodes, we restricted now to 3 electrodes. So we found out that only 3 is sufficient to analyze the ASD kids. So remaining 16s are vanished. So only 3 is sufficient now. We can, with the 3 itself, we can able to get 98% of accuracy with K. So that's how the first breakthrough we come across. So that's the one. The key finding is that central lobes gives the most discriminative region and 98.3% classification accuracy coming across into it. So in that achieved 8 to 38 out of 0 to 70 is this one. And in this range, 8 to 30 itself, I'm getting 93%. So that means remaining 40 hertz is contributing only for remaining 5%. So 93% is coming across 8 to 30 itself out of 0 to 70. So we are not worried about the remaining 50% of the hertz frequency range. Only the first 50% we are taking care of. These objectives, spatial focus come across. I am eliminating remaining stuff. I am taking care of only these 3 things. This is the first breakthrough, first publication. And the second one is my frequency band. So if you see that here, we have said that 8 to 30 hertz is the one which is giving the much more into it. Even then it was bandwidth is almost 22 hertz, 8 to 30. So out of this, doctors which one they need to do analysis part. So the next our end domain is that how we can contribute in it. This is also wide range in the bandwidth. How we can contribute for 0 to 8 to 30. How to do the analysis in it. So first thing is that we analyze the electrode from 19 to 3 we brought into it. Then we see that 8 to 30, how this can be reduced so that analysis can be much more better. So that's what the second thing. That's why we go for performance analysis of common spatial patterns in ASD kits using my ages. So we try to identify the common spatial pattern between 8 to 30 hertz in overall, along with we going to split this frequency range into the subbands of frequency. Which one is having the more featurings? Of course, you can see that 0 to 70 hertz having 98.3 accuracy, whereas 8 to 30 only 93%. When I divide into subbands, my accuracy of course will differ, it will decrease. But which one is contributing for more? So that's what we are looking to. That common spatial patterns are it's getting matched. Because previously only we focused on the electrodes, which lobes are contributing more. Now I'm going to focus on the frequency spectrum. So how it's going to contribute on it. So that's the first step. Since we are going to analyze on the frequency domain, you can see that first one is frequency domain analysis. One is go for power spectral density and FFT. Almost the same thing. We analyze on my power spectral density and FFT. Another is our wave rate transform, and in between we mentioned that. So literally what you did was CSP here stands for the common spatial pattern through the power spectral density or the peak to peak analysis. So all those things we did through. Literally, we come across these subbands, we analyze through statistical analysis. If you see that, in fact, we did the variance and correlation coefficients as well as LD. LD also will be changed later part of time. Likewise, we filtered and analyzed each and every sublayer of high frequencies. Okay. So, in fact, look like many matrix here. In fact, we have only 5 matrices to look into it. So, whenever starting point is there, we take both the typically developing kits as well as ASD kits. And if you see the 5 matrices, one is covariance matrix, another is the composite covariance matrix, another is Whiten matrix, S matrix, and projection matrix. So these are the 5 matrices we do the analysis part. At the end of the day, how the projection matrix is coming for ASD and this one. So what we did was, when the data is divided into subbands, we find the covariance across that. Then we do the composite covariance. From then we do for eigenvalues and eigenvector. From there we identified the Whiten matrix. Then we went for the S matrix. From that we do have my eigenvector. From that we do analysis with our covariance matrix. Then we went for our projection. So that's how we went into the analysis of projection of ASD as well as this one. So 5 matrices we come across and we analyze this pattern. So as I said earlier, this is completely on the frequency domain analysis part. So we come across TAM. So we went for the frequency domain analysis. So whatever I said, I just tried to have it here. One is finding over the covariance. First one is the covariance, normalized covariance matrix from that. Then the composite covariance matrix. That is, composite is both the typically developing as well as the ASD kit. Then we went for the whitening matrix. So the mathematical formulas and all I given it here. So you can always get it from the internet also. So the point what I wanted to tell you is that the analysis how it really helped us to move forward. Okay. So from that we went for the projection matrix, that is W equal to V transpose P. So at the end of the day, so projection matrix we had. So with that we try to analyze these stuffs. So whenever I have these things with me, okay, I put it to my LDA classifier and identify how much it is frequency domain common spatial pattern is giving, and we found out that it was accuracy is 75.43% when I do my frequency domain analysis. However, the same thing when I go for my, that's what I try to give it as a graphical thing, where the mutual information and along with my LDA. So we compare with all those stuffs. You can see that common spatial pattern variance and its mutual information is a correlation coefficient. There, the same thing with the LDA. When this is for FFT, this is for power spectral density. Likewise, we did it, and if you see that this is the one where I have 75.43 as the accuracy I have for this one. You can, sorry, it is, yeah. So it got 75.43 is the accuracy what we got for this one, for LDA. However, this is not 100%. We got around 93% of our accuracy. From 98 we dropped down to 93. But 75 is almost we lost 20% of it. So I don't want to lose the 20%. So we do the time domain also how it is works, and we went for it, and we got it around out of 93 we got achieved 94.73. Okay, so filtered our E signals peak to peak. We consider only peak to peak amplitude. Previously on frequency domain, now went for the peak to peak amplitude. We found out 94.73. That's what we got it here. You can see that it was 94.73 steps. So that's how we went for our here. And still we went for the time frequency domain mapping. So what is frequency domain and time frequency? We combine both and try to do the analysis whether it can really helps us to move forward. And we found that decomposition provides here a much more approximation coefficients here. And so all those things with that, we can find out that this is done and modify the coefficients here. And we found out that enhance discriminated analysis, and we achieved around 96%. This 96% means out of this remaining 93%, we considered that as 100%. Out of those 100%, we achieved 96.49% accuracy with respect to this, with the combined time frequency and spatial features of my stuff. So that is how we went into this one. So if you look into it, we got, you can see that here 96.49, that is peak to peak amplitude correlation coefficient with our SPM. Even though I tried with previously with LDA and all, we changed the classifier also from LDA to SPM, KNN and all. The KNN in fact here gives better results when I go for lobe identification. Whereas when I go for the frequency identification, KNN gives much less compared to my SPM. So that's why we went for the SPM here. Okay, so that depends on our. Very importantly, what we did was we do a lot of experiments. Frankly speaking, there is no principally, there is not something else we have to move forward in that direction. So we do a lot of analysis, and then only we come to the conclusion this SVM is better, previously KLN is better. So currently, whenever starting our research, we don't know that which one is going to give. What we did, one good thing is the literature survey that yes, this are the research gaps we identified. So we focus analysis on the direction, and very importantly, whether it yields or not, that come across with lot of experience. That with my lot of data into it. So next we went into the very core important point is the filter bank design. Okay, what we did. So whatever we did is something like filter bank. Whatever I said, the common spatial pattern about the white and matters, all those things are coming into it. And before that, I have the wavelet here. So each data I split into the different wavelets and I give it into the bandpass filter, and again I'm reconstructing it and giving it here. So based on that, since I'm regularized common spatial pattern, I'm bringing into it. I'm trying to match. That's why I have the correlation coefficients here. Last one after peak to peak amplitude, you can see that where is correlation coefficients are taken into account and how these are getting matched with that. So I'm going to have here importantly regularized common spatial pattern. So that this my objective is that I want to have the same 93% in my frequency band also. Currently I actually only 96% into it. So to bring it on it, we designed one more wavelet into it, and we try to analyze it, how we are going to get into it. So this wavelet decomposes the yield signal into multiple levels, each representing the different components. So with that, we can able to analyze much more detail into it, so that filter bank regularizes the CSP filter. So descriptive spatial features and all we can able to identify from this. In the peak to peak amplitude, the formula for the peak to peak amplitude, the logarithmic scale also given here. So how we have analyzed that peak to peak, that's what we are given. Likewise, the feature selections and the classifications, we take the different kernels. In fact, they say RBF kernels here to determine the frequency band. In fact, for the analysis part, as I said, we did a lot of experiments. We did a lot of kernel into it. Based on that, only we do all the analysis, and from there only we can see that SVM with RBF and kernel things, comparison of my filter bank. Okay, so all those things, if you see that here, this we got 98%. Previously, if you see that, we got 96% into it. So and my aim is that to approach my 100%. If you look into it, earlier 93% was there. Out of this 93%, I achieved only 75% initially. Then I come across, that was the frequency domain mapping. Then we come across time domain mapping, which get 90, it was 94, 95, 94%. Then comes time frequency mapping, that comes 96, 95, 96. Then we go for 98%, so that I am achieving 100%, that is equivalent of 93% of my actual 8 to 32 Hz. That's so my main aim. So because here itself, if I lose 98 to 75, that means I'm achieving only, if you think about it, out of 93%, I'm achieving only 78%. Literally, I'll get only 70% of my accuracy. I don't want to have, so I want to have the complete thing of it. This 98 means my actual 93% of 98% of 93%. So that's how we analyze from this. So we compare with our existing methods, solve those channels. Very important. Another important thing is that all those things they use 18 channel, much more larger channels. You see that whatever the last row is our proposed approach. We use only 3 channels. 3 channel means we already said we identified the lobes. Central lobe is the one which gives more information about the ASD. So all our analysis is based on these 3 channels. So all the frequency band analysis also from these 3 channels. So through that only we got the 98%. Okay. Whereas other people they use more channels and they got achieved only around 95%, means they got 16 channels into it. They got 92%, they got 96%, they got used 64 channels into it. But with all those things, we had a breakthrough with only the 3 channels. We can able to achieve 98% of 8 to 32 Hz. So that's what we focused on. So into it. So compared to the existing. So this is what the our second applications need. So one is we analyze our things, identify the lobes. Second is the frequency band thing. There we did a lot of analysis. Very importantly, lot of experiments in it, because experiments will give you a lot of meaning. Some, in fact, frankly speaking, a lot of our experiments went into garbage because those experiments results are not at all useful to us. We do a lot of analysis and only we got all those results. I'm projecting it as 98 and all with this graphs and all. But before putting into this RPF graph and all, I said we did all other kernels also. I didn't show that graphs because those graphs gives me only 80% of accuracy. There's no point in going with 80%. So we avoided all those things. We got all those things. As a researchers, we need to do a lot of analysis and stuff, what I want to see. And the next is that I say 8 to 32 Hz. I want to, as I said here, I want to go for frequency band identification. So 8 to 32 Hz is trying to, I'm giving me what are the technique I need to apply so that I get my 93%. That's what I applied so far. I just have the methodology now, how to achieve with these 3 channels alone good accuracy of it. Now, next layer is that you can see that frequency band. So machine learning approach to classification of this ASD using the optimal frequency band. Which band is giving more? Out of 8 to 30, that's 22 Hz bandwidth. Now you can see that here, now I'm including my wavelet transform, filter bank, regular CSP. If you see that until these things, all these things are my earlier approach. Up till the second approach, only all these things are. And here comes the stuffs where I'm going to split this 8 to 32 Hz into 4 Hz as a bandwidth, 8 to 12, 12 to 16, 16 to 20, and I split into 4 Hz and we analyze that optimal frequency band identification, then spatial filter stuff, and we do all this analysis, peak-to-peak analysis, fuzzy entropy, fuzzy description, then fractional fuzzy dispersion, and multifractional, then DFA. So all this analysis we did with that. Then we come across with the shape stuff. If time permits, I do the shape analysis and model training. Then we analyze the performance. So if you see it, it's a combination of the first 2 works. This is the third work. But we subdivided this band and we want to identify which one is giving more input. Of course, when I go for sub bands, my accuracy will be definitely it will decline. But at the same time, let us see to it how much it's getting declined towards, so that how can I match with my original stuff. So as we see that, we are going to focus on only the three lobes, central lobes. Out of that, only three channels, that is C3, C4, and CZ. So we developed already we have the CSP with us, and it is common spatial pattern analysis. So we are going to apply that to the different bands, so that we'll see how this could be giving a better results into it. So RBFL used to evaluate the frequency. Just I give the glimpse of it here. The result that we got is 87.5% on 12 to 16 Hz. We'll see how we do the analysis part. So when I try to do because analysis itself already given so in the first two stuff, and I try to, instead of giving the 0 to 8 to 32 Hz, we given a sub-bands to it. So the blue line shows my 8 to 12 Hz, this blue line, and the red line gives my 12 to 16 Hz. Likewise, the different frequency bands, whatever we did the analysis, we give it, and we try to check the analysis. And we found that it was 87.5% is accuracy happening in my 12 to 16 Hz. So in the analysis also, the doctor side, they don't want to concentrate on, they don't want to, we can leave it hand. So we can, so our aim is that to make it as happen, this 100%. Shall we finish it or? Okay. So our aim is to bring that 100%. We got only 98% with our previous all our stuffs with that. So in that 98, we do add sub bands into it. Which one is giving this 98% of it? Out of that, 12 to 16 Hz is the one which is contributing more, 87.5% contributing towards that. So we are going to, the lesser is something around, if you see to it, 20 to 24 Hz and all contributing very less. The last band is very less contributing into it. So we concentrate on the which band is contributing for more. So the features from 12 to 16 Hz is contributing more. So we do in-depth analysis of entropy analysis and this one. So with this, see, scientifically, whenever we say that it's contributing more, we need to identify why it is contributing more. So we do a lot of analysis into it. So why it is 12 to 16 Hz is special. So we need to identify, we need to explain scientifically to the research community that this 12 to 16 Hz is having more priority. Why it can? So for that only we do all these four analysis, entropy related features, that is detrended fluctuation analysis, then MDF analysis, and the peak-to-peak amplitudes. You see the DFE exponents, we try to take this long range correlations with the noisy range and non-stationary time series, and we analyze with that. So you can see that decrease in scale in exponent of alpha signifies that loss of long range temporal correlations. So whenever we do the analysis part, we found out that scaling exponent is getting decreased. And the strength of these long range colors are reflected here in my single scaling component of my DFA. So here each window means what I want to say is that each sub-bands contains local trend line. So double log diffusion plot depict my average fluctuation. So likewise, it identified my exponents here, and we went for analysis of my entropy related features. When I go for my entropy related features, and we see that single complexity irregularity under this happen, and embedded dimensions, tolerance level, and that point are equal to 0.15 of a standard deviation, and gradient, and also we consider it. So all those things, tolerance also we cannot take exactly. Some of them we are losing it, so we take tolerance of 0.15 of my sigma. Likewise, we take into analysis of my fuzzy depression entropy. So all those things and all we took into consideration. Then fuzzy dispersion of entropy, what we have was fractional order calculations and complex temporal dynamics also we take into account. So with all this analysis only we did, and we found out that the peak-to-peak amplitude and the beta alpha, best alpha frequency happened here. There we got our 93.59. You can see that spatial filter, and second is my peak-to-peak amplitude. entropy area where I got the analysis is this one, 93.5. So what we want to tell to the scientific community is that, so whenever I do my performance metrics in the SVM classifier, we found out that my fuzzy entropy is much more larger in this frequency band. That's the reason behind it why 12 to 16 Hz is giving much more significant difference in my AST classification. That's why we are trying to give into it. Okay, that's why we take into consideration 12 to 16 Hz with my all those stuffs. We can see the average decrease is 90%, and this comes to 92.5%. Previously we got 98, now it become 92 to plus or minus some 1.6% of tolerance. And we also did the cross validation, tenfold cross validation. That's very important. So whatever we do, we need to validate whether it is getting matched with the real-time data or not. So here, one good thing is that most of the analysis what we did is that in Python we have all the code with this. So only thing is that all the statistical analysis they have. Only thing we need to clearly give the data with the proper actual data. We work on the real-time data so that we get the proper analysis. That's how it has been. Okay. So the inference is that the wavelet-based filter bank combined with my regularized common spatial pattern is developed to identify this one. So this is really giving me achieved accuracy of 93.5. So if you see that here, all those things are contribute for 93.5 is contribute for my 98% into it. So if you look into it, the 98% is taken 100%. I got 93% into it. Almost we achieved 90% of accuracy. So we'll be aiding the doctors. Currently, we're giving to the Ramchandra Medical College their doctors that we analyze and we give them. So what they're trying to do is that they try. This is not scientifically proven. Scientifically, we have proven, not medically accepted methodology to diagnose or to identify the ASD case. However, we are validating our methodology with them, with our methodology with their common things, with their ISA. They currently what they are trying to do in Ramchandra was they give the training, occupational therapy, all these therapies they are giving it. After 6 months of training, again the students are coming, they go for evaluation. They do the regular evaluation with the Indian scale that along with our EEG analysis, and they cross verify whether our results are matching with their results. So once they are matching the results, most of them are matching with them. So from there, we are coming to know that yes, our results are validated across the Indian scale of autism stuff. So this analysis are currently happening into. Okay. So key findings is that out of 8 to 32 Hz, 12 to 16 Hz is the one which is contributing for more into it. And next we dig into it much more with the larger expansion, particularly with latest development in the scientific developments. The next objective is the channel identification rate. So we see that there are in the lobes, central lobes, there are 3 channels with that. One is the C3, C4 and CZ. So these are 3 channels which is contributing for my 98%. So we do an analysis called quantum-based machine learning approaches for ASD for identifying again common spatial pattern only. So our aim is to find out which one is maybe contributing for out of C3, C4 and CZ. And still we are moving on to it. So for that only went for quantum based, because why went for the quantum based was because the data is very, very limited. We are going to deal with in qubit data because quantum data only we are going to, it's small, only one electrode signal. How are you going to analyze with them? With the regular analysis of my frequency pattern or my lobes pattern, it will be very hard to analyze with regular stuff. That's the reason we went for the quantum analysis, that all these things are quantum based analysis. So directly we didn't take only one data. What we did was 2 data we taken. You can see the picture here. The top one, which is that you can see the 2 colors. This is what my central lobe. Central lobe out of that, this is my C3. I just zoom it out so that you can see that here. This is my C3, C4, CZ and C4 here. And which is C3 and C4 first taken for analysis. Then C3 and CZ. Then CZ and C4 is taken analysis. With only one data I cannot take. So I always take one as reference one. So C3 and CZ, C4 and CZ, then C3 and C4. So all those things are given, and whatever we give it regularized common spatial pattern with wavelet and peak-to-peak analysis. Then we do the correlation analysis. Then we go for SVM with quantum stuffs. Then we go for quantum support vector machine. Then QNN and neural network. Again, we did a lot of experiments. One is with the QNN, with quantum SVM and QNN as well as neural network. Which one is giving much more clear data into it. So that's how we went into. We took two data. With one data, it will be very hard. So when for two set of electrodes from the data, we went into it. So each data are C3, as I said, C3, C4, C3, CZ, and C4, CZ. We took into it, and we did the spatial filtering and all those things. Previously, we took 3-channel data. Now we are considering only 2-channel data. We just like that we didn't reduce to 1-channel data. We took 2-channel data and we are given it to identify which one is giving much more into it. And again, we did all the analysis part, and we found out that the C4 CZ, which is giving my 93.9% of it. So that's how the final results. I'm just showing it here. Then I go for how the analysis has been made to make it happen. So this is what C4 CZ of 93.9% has been there. Okay. So classifier wise, we did the 3 classifier to test this neural networks to leave complex linear pattern for C4 CZ. And quantum SVM, then quantum neural networks. These 2 things also we did to test it. So neural networks, we all know it with ReLU and sigmoid functions. We have come across that. When I go for that, what are the loss, binary entropy loss also we computed, and from that we identified how much probability of data is getting matched to that. Then when I go for my QSVM, the quantum SVM, so then the kernel tricks, we come across traditional kernel functions like RBF, other things also, and quantum kernel levels also we identified. And then machine learning, including QSVM, offers transformative approach, all those things analysis also we did with my quantum SVM. And regular stuffs, normally we know it very well, the x minus x bar exponentially, that's what we do. But here we do go for the qubit. So mathematically, this phi of xi is nothing but my qubit kernel matrix. It's the quantum feature map, phi of x feature map is there. And from that only we moved on. So here is the qubit one, which says that we analyzed with each and every qubit data. From there we give the data, then we go for quantum kernel. Then with the kernel only we supply to SVM to do the classifier. So from the feature extraction, we already have the C4, CZ values. We already have the 27 features, the absolute features, as well as the delta feature and delta features. From that feature map is we classify into the qubit part. That is given to the quantum kernel. From the kernel, we take into the SP. Previously, we had RBF kernel because that data is directly coming from the feature extraction. Whereas now, we reduce the data because we reduce the data into our C4, only 2 channels. Whenever we are reducing the data, we need to do much more analysis. That's why we went for the qubit data to analysis part. So, in the quantum neural networks, so traditional hidden layers are there, replaced with my quantum layers. So that's how we do with the analysis part of the quantum. So quantum layer are computed now. So this orders are passed to final output layer classification predictions. So these quantum things needed some more model to us. So there comes actually we had some hiccups because we need to run in the machine in the quantum computing, which needs a lot of machine power into it. So since it's doing with a lot of calculation with the qubit part, and so in such state, we had dedicated hardware and we did it in our GPU systems to work it well. So the remaining all those things and all, we did it in the regular stuffs itself. When it comes to QSVM alone, we went for our GPU stuffs to evaluate it. So during training, 20% of neurons of the layer randomly set to 0 to drop out the layer. Then 2 qubit quantum layers has been done. So to go move forward. So one is the, that's what we did the 2 parts here. One is the classical input layer where the same thing, you can see the quantum layer here. And 2, as I said previously itself, I split it into consisting of 2 neurons, so 2 qubit quantum layers. You can see that I mentioned 2 qubit quantum layers. This layers are split it up and given here, and the classical output layer we got it. So embedding in the measurements, before that we have circuit layer as well. So that's how we moved on. So from there, we found out that C3, C4 or C4, CZ or C3, C4, which is giving a better one. And we just found out that C4, CZ is giving much more better accuracy in SVM with neural networks and all. So that's why previously also we come across SVM and we go for the frequency band identification. And again in C4CZ also we went across the SVM to identify this. So performance, we also QCM, if you see all the stuffs with the SVM and as neural network and QSVM is comparatively better than any other stuffs with that. So this amplitude embedding gives me 94.7 accuracy into it. So frequency methods and peak frequency and all. So the Welch method, so see, as I said earlier, the previous also, we found that QSVM is better. Again, why QSVM is better into it? What is the analysis behind it? Why, what contributes QSVM is better? So we need to do proper analysis to say that why scientific community said this is better. So we are just not only saying is that why our publication was accepted was not, we are not only saying that this classifier gives the best results. This classifier gives the best results. Behind that, these are the reasons. I have the data behind this, gives this have characteristics of it. This characteristic is perceived from the artisan case. So that's the one which contributing makes the QSVM is better in this scenario. So that's what some analysis. I'm just quoting it here. Welch method, Stackwell transforms, peak to peak amplitude and all. Before that, we had some literature survey identifying which one is better into it. So I didn't give you the literature survey and all here, but those kind of literature survey we did it in between. So those things and all, I didn't add it up. So out of this only we identified, okay, this could be a better, and we did some experiments on it. So based on that only we did all the experiments. The Stockwell transform benefits the short-time Fourier transform. Why? Because I already reduced to only 2 channels. So I need to go for, I can't go for Fourier transform. I need to go for short-time Fourier transform. I am using the wavelet also. This is a Stockwell transform which gives the both Sttp as well as the wavelet. That's why I consider this into account, because I use common spatial pattern. I'm using the wavelet into it. This characterizes my scalable moving Gaussian window. So here it is there, adopts that. So this is that's the reason I'm going for Stockwell transform. So this transform maintains my direct and explicit relationship with my Fourier as well as this. I'm not losing the information of my frequency domain representation in my Fourier, but at the same time, I'm having my statistical measures also. So as a result, we can see that effective analyzing with non-stationary signals, because this is not a stationary signal in this. So ST is used to decompose signal into my time frequency components and my specific range. As we already identified that time frequency one, which gives me much more better results than the time analysis or frequency analysis. So this gives me both. So that's why we go for this one. So why we choose ST analysis is that this is the reason behind it. And the classification, go for Welch method to peak amplitude, peak frequencies here. And final is given to my QSVM, gives my 98.9. I can see it. So the peak frequencies, I'm each segment of 6 subbands of each segment. I just said one statement here. Each across 6 subbands across each segments, we have said it. Each segment 6 subbands means 12 to 16 hertz, 8 to 12 hertz, 16 to 20, 20 to 24. All this across 6 subbands. What we mean to say that. So we put across all these 6 subbands and we found out how this is better in each subbands. So from that only we identifying this is better. So that's what we have mentioned it here, that 98.9% is coming across in PSVM. Performance metrics here, different feature combinations I have and found out. So inference is that the wavelet filter banks regularize the common spatial pattern to have these things, and peak to peak amplitude is having this one to give 98.93%. So if we look into it, in fact, I have just given the 3 objectives here. One is all about lobe identification. Next is the frequency identification. The third one is our C3, C4. And still the next stage is still we are working on. Currently, all these things are separate analysis we have. But currently, what the doctors are feeling hiccup is that each machine is separate, this analysis is separate. Currently, all the analysis are happening is offline only. But the doctors from Ramachandra doctors, what they are feeling is that if it is a one machine, they can have it as a one analysis machine, which can able to give the results is better. Currently, we are working on the direction. Again, we are going for the DST funded one to have support our initiative in it. And we are trying to make the combined device along with the EEG. So what our analysis also going to be in a hardware, in an embedded board. So STM board only we are considering it. So that all the EEG signal, whatever they captured into it, so all these filters, all those things going to be as a filter bank into it. Through that, and we are going to take analysis and it's going to give us data to them only in this part. Currently, it is they leave it to the doctors, it gives the data, and they are approaching this, the data is given to us offline, we are analyzing it separately and giving it. Instead of that, let the data comes as it is, and our analysis also will come as another set of data to them. It will be really helpful for them to correlate these two to give the proper analysis. So what they did was, currently we are focusing on that direction and we are making into it. This is one of the neurological disorders in the analyzing my EEG signals of this stuff. One is autism. Likewise, there are other things also there. Something nowadays it's giving much more analysis, anxiety analysis, and of course, well-known problem is the cerebral palsy. So all those things are coming up in the upcoming days. So those analyses also still left out need to be much more, and of course, epilepsy. Those are also need to be explored, unexplored areas we need to focus on. If you ask me where we can focus on in those areas, we can see, we already have some analysis part with respect to EEG analysis here. With this, our data is only our autism spectrum cuts data only we have this. However, if we have the epilepsy patients or the other patients' data, their analysis will be something will be different. That will be really helpful for other community also. The research domain, we can say that we can focus on those directions. Okay, so there's some of the references I gave it here to move forward. Okay, so how we have come across. In fact, we come across 3 publications in it. One is the lobe identification, next is frequency band, and another subbands along with the C3, C4, we come across that. The third one and fourth one, we are working it on the going for the devices, and still the work is going on with this. That's how we have carried out our research here. I just conclude here my stuff.
So things and
yes, sir. Yes, sir. Yes, sir. Yes, sir. So when we have this data with this, so I think we mentioned it. We have the combined data from the 4 dimensions. For example, we have the two channels data with this C3, C4, and along with we have some features with this. So through features only we have all those things, and we have 4-dimensional data. What we're trying to say is that 1-dimensional data coming from the this one, the absolute features, then direct features, and the delta feature, and the fourth one is the combination of all the things. So when we have all the typical developed children as well as this one, so we try to bring into one loop, because that's do a lot of analysis part. So we bring the 4-dimensional data into it to analyze this one. When you move into, I think Sarah was saying that maybe you're moving towards university status in another upcoming years. When university status comes into play, from management, there will be a lot of pressure, will be on us as a faculty community to going towards the research. So we need to equip ourselves in moving towards it. So maybe if we explore it, maybe in the upcoming days, it will be really helpful for your career as well as this one. Maybe in another, before 10 years, we are not into this direction in VIT. In the 10 years, we have moved across a lot. So 10 years before, if you ask me that, if will you get a DST funded project that is and all, far away from me. So it will all happen because one is management is supporting as well as management pressure also there. They will ask us to move towards it. That time we need to have a clear vision. In fact, those days we don't have it, and we fell into it and we found out. Fortunately, we had some avenues now. I think it will be really one or 1 or 2 years we'll be getting into that position that you will be pressurized to go for a funded project. That time we need to have a proper good thing to move on. Yes, sir. QSM, quantum SVM, sir. Quantum SVM. So we have the quantum. That's what we say that in that picture. I've shown you that the kernel itself. Before giving to SVM, we have the quantum kernel. So here we see that qubit. So through qubit is the one sort of data what is given is very limited data. So with the minimal data, we are trying to give it as feature map. From that, it is getting mapped because we reduce the data here itself. Because we analyzing only two set of data, C3 and C4. We are not analyzing the complete channels. We are analyzing only two channels. So that need to be populated. So there we are analyzing even small part of it. That's why quantum itself very small area. So that we are giving to the quantum computing and we are making it as data and we are going to process it. Otherwise, with less limited data, forming kernel itself will be difficult one to do.
So the session of today is so already see the easily use case. Okay, so bring it to the Sttp. Minimum 5 use cases really to me my knowledge and they schedule the condition to access the data
Yes, you have that facility. I forget it. You have medical college facility. In fact, we struggled a lot. Yeah, Sir knows this because when getting this data, he was traveling from VAT to Ramchandra almost every week to do that collected data.
So, you will get the fact that we need to have it is so